Welcome to the session on projectiles, projectile motion formulae. The objectives for this session are to derive formulae for time of flight, range, and greatest height for the equation of the path of a projectile. We need to be able to derive general formulae which are related to a particle projected from a point on a horizontal plane moving freely under gravity. Let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's begin by taking a look at the scenario for this example first. A particle is projected from a point with initial velocity u meters per second at an angle of elevation alpha and moves freely under gravity. Resolving velocity of projection horizontally and vertically, upwards being positive, we have horizontally ux equals u cos alpha, as shown in the diagram, and uy vertically equals u sine alpha, as shown in the diagram. So here's ux equals u cos alpha, and here's uy equals u sine alpha. Now let's take a look at part A. We are required to show that the time of flight equals 2u sine alpha over g. We are going to need ux and uy. So considering vertical motion, we have uy equals u sine alpha. The displacement is 0. Ay, the acceleration under gravity, equals minus g, since the vertical direction is upwards as positive. And we are required to find the time of flight, t. So which of these equations of motion should we use? We need to use the one which includes all the letters u, s, a, and t in it. And in particular, it's this one, s equals ut plus a half at squared. So plugging everything in gives us u plugged in as shown, s equals 0 plugged in here, a equals minus g plugged in here, and time t unknown plugged in as shown. We can now rearrange and solve for t. To give either t equals 0 or u sine alpha minus gt over 2 equals 0. Therefore, we have that t equals 2u sine alpha over g, since t equals 0 occurs at the start. Now let's take a look at part B. We are required to show that the time to reach the greatest height equals u sine alpha over g. So let's solve this. The time for the entire journey from part A is t equals 2u sine alpha over g. Now the maximum height occurs at half time, so t, or time taken to reach the maximum height, equals a half t. And this equals u sine alpha over g. And therefore we've proved part B. Now let's take a look at part C. We are required to show that the range of the horizontal plane equals u squared sine 2 alpha over g. So let's solve this. If we resolve horizontally, we have that ux equals u cos alpha, as shown here. S subscript x equals r, the range. T equals 2u sine alpha over g from part A. And the horizontal acceleration, ax, equals 0. As you can see from the equations of motion, the only equation which includes u, s, t and a is s equals ut plus a half at squared. So let's use this equation to find the value of r. So plugging in all the values, u goes here, s equals r goes here, t goes here, and a equals 0 goes here. And tidying up gives us this expression, 2u squared cos alpha sine alpha over g. Now we apply the double angle formula. 2 sine alpha cos alpha is identical to sine 2 alpha. To give us that r equals u squared sine 2 alpha over g, as shown here. And so we've shown that the range of the horizontal plane equals u squared sine 2 alpha over g. Now let's take a look at part D. We are required to show that the equation of the trajectory y is as shown. So let's solve this. If we resolve horizontally, we have u subscript x equals u cos alpha, s subscript x equals x, as shown in the diagram. We will also need to find t in order to find the equation of the trajectory. And we also have that the horizontal acceleration is equal to 0. So let's use the formula s equals ut plus a half at squared, as this is the only equation which uses all of the letters shown. In other words, u, s, t and a. So let's now plug everything in. We have u plugged in as shown. T is unknown. Acceleration equals 0. And s equals x. And this term disappears. So we have 0 here. And solving for t gives us this expression. Now let's use this expression for the next part. Resolving vertically, we have uy equals u sine alpha and sy equals y. And here we're going to use t, which equals x over u cos alpha. And of course, this value of t was from the previous calculations. Vertically, acceleration equals minus g. Notice that we're taking the upward direction as positive. We have letters u, s, t and a, so we use the formula s equals ut plus a half at squared. We plug in s equals y, u equals u sine alpha, acceleration equals minus g, and a half stays as it is, and t is here. We'll substitute that in a moment. So we can now plug in the value of t, as shown, to give this expression. And tidying up, gives us this expression here, which is what was required for part D. And so here's a summary of all our equations. We can use these formulae to solve other problems by substituting values into them. However, we can also solve problems using the techniques we used to prove these formulae. Let's now take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's now take a look at part A. A particle is projected from a point with speed 7 meters per second at an angle of elevation alpha and moves freely under gravity. When the particle has moved a horizontal distance x meters, its height above the point of projection is y meters. We are required to show that y equals x tan alpha minus x squared over 10 cos squared alpha. Notice that the horizontal component of the initial velocity is 7 cos alpha. So if we resolve horizontally, we can use the formula distance equals speed times time, since there is no acceleration in the horizontal direction. And so we have that distance, x, equals 7 cos alpha, the speed, times time t. And therefore we have that t equals x over 7 cos alpha. If we now resolve vertically, we have that uy equals 7 sine alpha. This is the vertical component of the initial velocity. We also have that the distance vertically, or displacement vertically, equals y. Time t equals x over 7 cos alpha. And the acceleration due to gravity equals minus g, since we're taking the upward direction as positive. And so we have U, S, T, and A. And again, we ask which of these formulae we're going to use. Since S equals UT plus a half AT squared uses all of these letters, we will use this formula. And now we can plug in all the expressions. So U equals 7 sine alpha goes here, S equals Y goes here, T equals X over 7 cos alpha goes here and here, and A equals minus G goes here, to give us this expression. And tidying up, and plugging in G equals 9.8, gives us this expression, which is what was required for part A. Now let's take a look at part B. Given that y equals 0.8 when x equals 1, find the possible values of alpha. So let's solve this. From part A, we have this expression for y. And so we can plug in y equals 0.8 and x equals 1 into this expression. X equals 1 goes here and here, and y equals 0.8 goes here. Then tidying up a little gives us this expression. And notice we have tan alpha and sec squared alpha. You might be able to spot that you could convert sec squared alpha to something involving tan squared, and this will then give you a quadratic in tan. Like so. And rearranging and tidying up gives us this expression, so we can now either use the quadratic formula or factorize to solve for tan alpha. And factorizing gives us tan alpha minus 9 times tan alpha minus 1 equals 0. So either tan alpha equals 9 or tan alpha equals 1. And this implies either alpha equals 84 degrees or alpha equals 45 degrees. This brings us to the end of this session. If you have understood its contents, you should be able to derive the formulae for time of flight, range, and greatest height for the equation of the path of a projectile. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.